Thank you, Paula. Hi, everyone. Great to be here. So as Paula said, I'm going to talk about the importance in model design in building a computer vision application, and let's simply start. So I'm going to talk about the common barriers to model deployment that are coming from the model design and key elements for building production-grade computer vision models and best practices for model design, and what is neural architecture search, and how can we use it to design a better model. So AI has a barrier. Designing state-of-the-art deep learning models is very complex, is taking a lot of resources, both from the training side and also the model design, hyperparameter search, collecting the data, labeling the data, and everything is so challenging. And we try to think about how the future will look like in terms of deep learning development, and what are the key elements that will be automated, that will be replaced with better practices and processes. So the common barriers for deep learning deployment, first of all, is the accuracy. We all look for having the best accuracy we can achieve. The second one is unsatisfactory performance. And when I'm talking performance, I'm talking on inference performance and the ability to take those models to be deployed on the target platform that we are interested. And in computer vision, we are mostly talking about taking those models to the edge. And the last component that is related to these both aspects are the long development cycle, where we work on iterating on the model and the data and improving the accuracy, and then we want to deploy. So we have to work on the inference performance of those models, and all of these taking a lot of time in order to get a project to complete and get a model to production. And we see it with DESI all around. When we mainly focus on computer vision on the edge, we see companies struggling with getting to the level of performance that they're interested in and how it affects their business. So we see video conference application company that needed a boost. We see mobile application that are trying to get better performance or need to work in the cloud, and the inability to scale surveillance cameras into Jetson in the right number ratio between the number of cameras and number of Jetson that are running those workload. And when we look about the model design, what we see is that since 2012, where AlexNet introduced, we see constant improvement of the top one accuracy of those models that break time after time the state of the art on ImageNet. And here we talk about image classification models tested on ImageNet and also trained on ImageNet, and we see that it continuously improves based on new techniques for training models and for designing models. And the idea here in this curve that the data is fixed. ImageNet did not change, and what is improving is the designing of the models and how to train them. And we see the same in object detection on COCO, where the average precision is improving all the time. And here the curve is even more steep than the example that we saw earlier. By the way, those curves are from papers with code. But we are not interested only with accuracy. I gave the performance of the importance of latency or inference performance or throughput. And what we see is that when we put all of those models in what we call frontier, where on the y-axis we see the top one accuracy, and on the x-axis we see the latency, we see that there is some barrier in a trade-off between the accuracy and the latency. So when we want more accuracy and we go to the larger efficient nets, for example, in this case, we get lower performance or higher latency. And this is a trade-off that we need to know how to navigate and know how to break. And just to understand how this trade-off is even more complex than we think, usually performance is approximated by number of parameters or number of flops, but these are not good representative numbers. And our recommendation is to actually measure the latency on the target hardware, including all the inference stack that we're using, if it's quantization or compilation, in order to really understand how the model is going to perform on the hardware. And what we can see here is an example how two different hardware types from the same manufacturer, in this case K80 by NVIDIA and V100, and two models, ResNet 50 and EfficientNet B0. So when we look on the K80, the gray bars, what we can see is that the EfficientNet B0 is lower latency, has lower latency than the ResNet 50. But then we consider the same two models on the V100. What we can see here is that the ResNet 50 is faster. So that's a question: how can we know which model to take? And the answer is we need to measure on the target hardware in order to understand how the model will behave in terms of latency or performance on that hardware. And by the way, ResNet 50 and EfficientNet B0 have quite similar accuracy on ImageNet. And the idea here, if at the end of the process we understand which model will run faster on the hardware, it's quite problematic to run all that process and then understand, build that EfficientNet, and then understand that it would be better to take ResNet 50 and build again on the ResNet 50, which is obviously a simplified example for that. But the idea is to take all those considerations from the production environment early on in the development process, where today we select the model, we annotate the data, we select the model, we train the model, and only then we start to think about how to deploy that model and how to boost the performance of that model. But alternatively, we recommend to work in an approach that is called production-aware model development, where early on in the process, we at least measure the performance of the algorithm, but not only measuring, but also optimizing and taking actions with respect to model performance in order to get the required or the desired performance level, and not going through the entire development life cycle, understanding at the end that we cannot deploy this model. So this is kind of a new approach that we're leading, and thinking of that, it makes a lot of sense to take production consideration early on in the development process. And the idea is not only to look on accuracy, which is here, but to look on all the metrics and all the production constraints that we have early on in the model design phase. Because we want to know that the model is not too big. We want to know that it meets the latency. We want to understand that it can compile. For example, some models has ops that are not supported into some graph compilers. We want to know that it can quantize well. And obviously, we want to measure that inference performance on the target hardware or inference environment. So the idea of taking all of those into consideration in the model design is nice, but designing models manually is very, very complex. So it requires us to adopt some tools and algorithms in order to do that better and faster. And the idea is to develop with NAS, neural architecture search, which I will cover how NAS is integrated into the DESI deep learning development platform. So we call it AutoNAC engine. It's a hardware-aware neural architecture search engine for deep learning inference efficiency. The idea is to design models that can run better in production while taking all the consideration that I discussed earlier. So the idea is that we need to understand what task we're trying to solve, what data characteristics do we have, what inference environment and hardware we use in order to understand what is going to be the performance. And then we feed all of this to the AutoNAC engine, and it generates a new model, a new architecture that can run in the performance requirements for all the components like accuracy, latency, throughput, model size, and memory footprint in order to reach production at the end of that process. And that's simply the idea of the process, and we'll soon dive into that AutoNAC engine component in order to understand how this magic happens. But let's first get some motivation for the results that can be achieved. Here we see the same curve with Y, the top one accuracy on ImageNet. On the x-axis, we see the latency of an Intel Cascade Lake Cloud CPU. And what we can see is that we see here all the ImageNet open source, or most of the ImageNet open source models from MobileNet, V2, V3, EfficientNet, RegNet, RepVGG, Google Nets, ResNets, and EfficientNet Lite. All of those are here in some trade-off between accuracy and latency. And what we can see that based on the AutoNAC, we can generate networks that we call datasets, which those datasets are outperforming any open source model with a wide margin in the trade-off between accuracy and latency. So if, for example, we consider the EfficientNet Lite B4, which is here, and we want to replace it to a better model, what we can take is something like datasnet 6 with similar level of accuracy, but running at inference more than 2x faster, or any of those datasets in the top left quadrant that improve both accuracy and latency in different proportions. And the business impact of using those models is reducing the inference cost significantly and enabling inference on any edge device. So let's understand a little bit about the automated neural architecture construction algorithm and how it works. So as I mentioned earlier, AutoNAC receives 3 inputs: user's dataset, baseline model, which we will call it A0, access to the target hardware. Let's assume for this example that it will be a Jetson Xavier. The AutoNAC objective is to find an optimal architecture A star that preserves the accuracy and maximizes the throughput. So we have some baseline model, for example, ResNet 50, and we want to improve that ResNet 50 to improve the inference performance, the throughput, but with the same accuracy of that ResNet 50. AutoNAC is aware of the data, hardware, and even low-level graph compiler, and I will explain it. And all we need to understand is that equation that is written here. We're looking for A star. A star is an optimized architecture from a calligraphic A. Calligraphic A is an architecture search space consisting millions of architectures, optionable architectures to choose from. That A star is maximizing the throughput, subject to a constraint on the accuracy. So what we want to have is that the throughput on the hardware of that A will be maximum, subject to preserving the accuracy of that A on the data D compared to the accuracy of A0, which is the example of ResNet 50 that I took. And let's decompose this into 2 components. One of them is the throughput age. So how can we know the throughput age on the hardware age for a given architecture A? We simply measure that. It's quite easy to measure the performance, the latency, or the throughput of neural architectures. You don't need to train them. You can do it with random weights in most cases. And you can obtain or get those numbers of throughput for the candidate architectures pretty easy. But the more complex thing is to find the accuracy of an architecture on a given data set. The accuracy of an architecture, in order to understand that, we need to train that architecture, which is quite expensive, especially when we talk about a problem of selection of architecture out of millions of candidate architectures from calligraphic A. And then it becomes very sophisticated. And for that, I cannot get into details, but we have an AI-based model that can estimate whether the constraint about the accuracy is preserved or violated. So the idea is to approximate this second thing with an AI model. And if we do that, we can transform that training problem of training a lot of models from A, calligraphic, in order to understand their accuracy, to an inference problem. And we all know that inference is cheaper by 10 to 100x. And by that, we are shifting the problem from becoming a training problem into NAS to an inference problem into NAS, which helped us a lot to build a commercial offering based on that NAS algorithm and running really fast compared to AutoNAC solutions. So let's understand a little bit about where this NAS, neural architecture search, sits in the entire space of model optimization. So if we look on the bottom, we see the hardware. We can choose any hardware we would like: CPU, GPU, JetZone, FPGA, embedded hardware, etc. The only requirement for AutoNAC is the ability to measure the latency or the throughput or even the power consumption if we want to optimize that on the given hardware. On the graph compilers layer, we see solutions such as TensorRT, OpenVINO, TVM, and others, TF-Lite, AutoNAC, and more. This is a layer that defines how the graph of the neural network is implemented on the given hardware, how it will run on the hardware itself. On top of that, we have the model compression techniques such as quantization. Quantization today usually integrated or supported into the graph compiler layer. For example, in TensorRT, you can quantize the model into 16 and 8-bit. Also in OpenVINO, you have those options. So those two layers are kind of merged together over time. And at the top, we have the neural architecture search or model design techniques that I mentioned. And just to understand the importance of those components, so in the MLPerf is a performance benchmark for deep learning algorithms and hardware types. So last April, we collaborated together with Intel on MLPerf, and what we see is that when we take, it's hard to compare results in MLPerf, but when we normalize the results for per core, per CPU core, what we can see is that the baseline is doing 14 images per core per second. Intel submission and many others that submitted on CPU get to 50 images per core per second, which is about 4x on that result. And DESI, when leveraged AutoNAC, including OpenVINO, which is a graph compiler, and 8-bit quantization, getting 5x on top of that. So what we can understand is that the control on the model design is very important part on that stack that you cannot ignore when you design production grade application. It's really important to take into account the model design and the structure of the model and the performance behavior of that model on the target hardware that you're looking to take. By the way, I didn't mention, but all of those are compared to ResNet 50 on ImageNet. So that's the benchmark in MLPerf that we have participated with those results. So to summarize, with DESI and AutoNAC in general, you can enable inference on edge devices. You can reduce the inference cost if you're working in the cloud by improving the throughput or the hardware utilization of the hardware that you already pay for. You can improve the user experience with better performance at the edge, for example, in consumer applications that running deep learning in real time. And you can also simplify the development and shorten time to market by not needing to do those manual iteration time after time, training more and more models in order to improve another 0.5%, another 2 milliseconds in latency. You can do that automatically.